Okay, so just to make sure you're in the right room, because maybe the other talk is going to be more interesting, I want to do a very quick disclaimer first. There won't be any code in this session. Okay, so this is all theory. I'm going to talk for 3 hours, and I need something to draw on. So no, I'm joking. I'm joking. Otherwise, my attention span is going to be like more than 15 seconds. So that's my name. That's an old picture. This is what I do. I work on Power Apps. Who's been using Power Apps or has used Power Apps before? Okay, so if it's broken, it's probably my fault. But those are my contacts. I'm also on LinkedIn, but check me out. So in this talk, I'm going to try to give you definition of what resiliency is, see some of the things that can go wrong with distributed systems, and some of the strategies that we can apply to just build a safety net. So if by the end of the talk I didn't give you anxiety, I didn't do a good job. So that's from a dictionary what the resiliency is. In a nutshell, it is the capacity to recover quickly or to adapt to change. Resiliency and resilience are technically they're synonyms, and they're used interchangeably. So resilience is more common; it's preferred in academic section environment. But what it means for us, like software engineers on our services. So a resilient system is a service or is a system that can recover gracefully or effectively, actually, after problems. So having a resilient system means that our program doesn't crash like badly. They should handle errors, like as I said, gracefully, and they should avoid catastrophic failures, meaning that the users maybe are noticing the issue, but I mean, for them it's not a big deal. And because in some cases, software that is not resilient can be also dangerous. I mean, most of us are probably like web developers or doing, I don't know, who's doing software for MRI machines and scans. If you don't make the service there, the software there being resilient, you can actually create a lot of damage. And again, resiliency is not just on software; it's also on hardware. We'll discuss some of the caveats a little bit later on. But I mean, adding more power supplies to your servers is a form of resilience. So, find the similarities. British Airways, 2019, Google Paris, 2023. What do they have in common? In 2019, British Airways had a bug in one of their systems, and in both the Heathrow and Gatwick airports, more than 100 flights just disappeared from the service, which means that a lot of people were left stranded in the airport. That's not nice. 2023, there was a water leakage. There we go, hardware resilience. Water leakage in the data center, one of the data centers, Google Paris. And with the leakage, eventually caused a fire in one of the rooms, and then poof, a lot of data got lost. Where I'm getting to this, even big companies have problems, okay? That's just a matter of fact. What it matters and what changes is that they have more processes, and they're capable to understand what's going on and to react and make sure that these things don't happen anymore, which usually happens through a form of post-mortem. What's the problem? Why it happens? What's causing it? Let's make sure that doesn't happen anymore. Bottom line, if they have these problems, you will have them, so don't stress. It is going to happen. So your job is to plan, do your best, and just embrace the Murphy's Law. So you might not think that, but this is a distributed system. We have two computers talking to each other. I guess that mostly everyone in this room started with something simple like that. It's basically just a web app, okay? A server that talks to a DB. But still, in a nutshell, this is the easiest form of a distributed system. Over time, things can get like out of hand, and get out of control, and you may end up with something like this, which means that probably your business is healthy. So it's a good problem to have, but no matter what, you need to plan for resiliency, because things can get even worse when you have this type of architectures. So what can possibly go wrong? There's a wide variety of things that can go wrong. We can have network cables that can be just severed. And actually, it happened not so long ago in Finland, I believe, or anyway, North Europe, they have like cables underwater that got just severed mysteriously. Allegedly, was sharks eating them, biting them. Allegedly, very angry sharks. So anyway, it can happen. There can be a misconfiguration with your DNS. So all of a sudden, poof, your websites don't work anymore. It's very common. Or another thing, and this is a true story, whole servers can be just disconnected, packed, and shipped by mistake. So somebody just went into a room. I like that. Poof. You know. We have two golden rules, basically. There might be more, but let's start with these two. Networks are unreliable, and transferring data takes time. Let's get into the details. There's no cloud. Okay, this doesn't exist. It's a fantastic thing. You know, you write your own code, you write your infrastructure's code, you know, your nice script, and then you offload the burden of the infrastructure and the operations to your cloud provider. And you don't care anymore. That's amazing. I do it all the time. The fact that you do that doesn't mean that your software doesn't run anymore on actual hardware. It might be, like, yes, it might be Docker container running on another layer of containers plus virtual machines and so on, but still you have physical machines. It might even very well be a Raspberry Pi under the desk of somebody, but it's the cloud, you don't know. So you still have physical machines, you have cables, you have routers, you have switches, and the worst thing of all, humans that are managing these things. So that's the worst part. So again, there might be several reasons why your remote calls are failing. There might be, I don't know, the server crashed, too many requests, so it's overwhelmed, or again, hardware problems. So bottom line, again, don't expect the network to be there helping you all the time. And again, the second one, time is unavoidable. I've seen people saying, and this is a true story, saying, yes, they want to transfer data. It's not transferring. I mean, I send something and magically appears on the other side. So if I'm making a remote call to Australia, they immediately have the payload that I'm transferring. So first of all, we have the speed of light. So still, there is like a physical limitation to the transmission. And so unless you're really working with like assembly, we are shielded by using high-level languages. We are shielded by a lot of details. When you send something over the wire, your message has to be converted into a format, has to be split into different packets, has to be transmitted over the wire, and then on the other side, you have the reverse operation. So the packets have to be like reassembled, they have to be parsed, they have to be reinterpreted. These things don't come for free, you know. So there's still time. Then we have the speed of the computers that are involved. You have the distance between those computers. You have the time, the type of the network. You have the size of the data. And then there's the worst thing of all. Like humans do, also machines don't have the same perception of time. So even computers in the same room might be running on a different time zone, or even like small discrepancies in the hardware can lead to different milliseconds, and those can make a big difference. I'm getting caffeine from there, and this is amazing. So don't make any assumption on the perception of time from your end to the receiving end. Now, I've never in my life heard anyone saying, I don't want my system to be resilient. Even if you're writing like a small POC or prototypes, throwaway code, you still want some form of resiliency. You might want to do error checks, you may want to do input validation. If you're using stuff like C, C++, you might be doing memory management. I know you young folks are using Rust these days. So. But anyway, these are all strategies to make sure that your programs don't crash. Now, the real question is how much resiliency you want, how resilient you want your system to be. And the answer is all about cost management. It's basically a trade-off. So it can be a financial cost. Send you the slides, I know you're interested. So it can be a financial cost because you're getting a larger bill from your cloud provider because you're getting beefer machines. Or it can be a time cost because you're assigning an engineer to work on like improving resiliency, and then this person can't work on other functionalities and improve the rest of the system. So again, it's always a trade-off between the cost and the chance that you actually get something in production. Basically, it's a bet. You're betting against the probability that something bad will happen, which will actually happen. So again, if you have an e-commerce and you lose an order from time to time, yes, it sucks, but I mean, okay, it can happen. If you have an MRI machine that gives out wrong results, you definitely don't want that. So now we're taking a few simple strategies that we can put in place. First one is like scalability. So I guess everybody here knows, at least has a sense of what scalability is. It plays a crucial role in distributed architecture, and it can allow us to also grow elastically based on the load. We mainly have two strategies. So let's just give an example. We go back to our amazing distributed system. This is somewhat of like going back to monoliths. Eventually, people will go back to this thing, I'm sure. But so easiest example, you have that's your infrastructure, and you have an e-commerce, and then it's Black Friday. So boom, you have all the users logging in and trying to buy heavily discounted stuff. Most likely, after a little bit, your web app is gonna just sit down and say, I can't do this thing anymore, and stop serving requests. So what do? Again, it's a trade-off. You can even very well say, I don't do anything. Let's live with it. That's okay. I know a person who has a very successful website about cost of living in different type of world. He has truckload of visits every single day, and that's exactly what he does. He doesn't do anything. 500 error, go check it somewhere else. First option, the easiest one, is scaling upwards. So normally, even if you're like both on cloud or on premise, you have a certain degree of freedom. About most likely, we're talking about scaling, increasing the amount of memory, getting stronger and faster CPUs, or perhaps upgrading your SSD drives with something fast. It's usually the first thing that we start doing, even though we have some considerations to make. First of all, we will have we will very soon hit upper limits. So there's just a fixed amount of RAM that you can install on the server, and then otherwise you're stuck with that. First. Second thing, is going to be very expensive at some point, and it's going to be much more expensive increasing the hardware rather than adding a new machine altogether that's basically commodity hardware. So it's like way cheaper. And then there's the last thing, which is the worst part. If you have a single server and you want to scale it up, you have to take it down. So your application is not gonna run during that time frame. So you're not gonna serve any traffic. So the other option is to scale out, which basically means growing the number of machines and distributing the traffic all over these new nodes. It can be done elastically, so based on the traffic, you can add and remove more machines. Usually, cloud providers will help you. You can set up rules based on metrics, like CPU, number of requests, and so on and so forth. The other issue is that your infrastructure anyways becomes more complex because all of a sudden you need a load balancer to just spread the load across the nodes. And maybe you didn't have the need before, but now you actually have to. There's no other way. And also more machines, more nodes mean more effort to manage the operations. Then there's another big difference between scaling up and scaling out. It's the network latency, because you're adding a new item, the load balancer, so you have an additional network hop, and it's also an additional point of failure. Now, this overhead might be negligible, but still there are some circumstances where like even just a nanosecond will count. Then the other thing, to me, this is probably the most important. When you want to scale horizontally, your application has to be stateless, which if you don't plan it from the very beginning, it's quite complex to achieve, midway through. So picture this: you have a user logging on your application, and on your single server, or on the server that you have, you start storing some state regarding that user, which might be even a simple thing like I don't know, user preference on the UI, the call, or even the entire cart of that e-commerce. So storing the state on the node that is processing the request works only if you either have just one node, so you're not scaling it horizontally at all, or and this is tricky to achieve, it's doable, the load balancer is rerouting the requests always to the same node. It is doable, but it's prone to something called hot partitions. You basically might end up having the same node serving too many users, depending on the algorithm that you're using for reroute. Normally, what is used is consistent hatching in this case, but it depends on the load balancer that you have. So if you have instead an application that doesn't store any state, you have to rely on an external storage. It can be a cookie, which you can use if the payload is not too big, or you're not storing any sensitive information. I mean, you can store sensitive information in a cookie, but it's just not a good idea. And the other option is a caching server, like Redis, for example, which can be distributed as well, but costs a lot and is another piece of infrastructure you need to manage. The second strategy is going to be retries. So again, if your call fails, there's a bunch of things that can happen. Maybe there's just too many calls that the server is receiving, so you're getting throttled, which we'll be talking about that. Or the server is down for maintenance because they're scaling up. So in those type of situations, suppose you're making a GET request, retrying might make sense. But we have a bunch of questions. So first of all, how many times do we retry? How long do we wait between the different retries that we make, or we retry immediately? Like, are we there yet? And if we retry too much, too hard, are we actually causing problems to servers? It's a thing. But first of all, we need to understand, is it worth retrying at all? So again, you're making a GET request, you want to pull out some data. So if the server is overloaded, perhaps it is a good idea to just retry your call. But at this point, if you're using HTTP, your client has to be, and at this point it's up to you, the caller, your client has to be smart enough to understand what kind of status you get back. Assuming that you can actually trust the server and that who's implemented the server is using the right HTTP status, which you might not give them for granted. So that's another thing. So again, you have to make an analysis on the status that you get back. The other aspect is, if you get a 404, is that actually true that the resource does not exist? Because if eventual consistency is a thing, it might be that it does not exist now, but it will exist in some time. how much is that? So 404 is controversial. Maybe when eventual consistency in place, probably a 202 is more like recommended. But we need to make a distinction here between a bug, you misspell the URL, and the resource does not exist yet. Again, how do you do it? If you can contact whoever wrote the server, that's just a good place to be. So how many retries? If you keep retrying, you're just generating more load on your server. Yes. Can you just speak louder? How would the server know if it doesn't exist yet? Oh, the server knows because it's the one responsible of generating the data. It's the client who doesn't know. Okay, but as an application developer, if you're in doubt, because perhaps it's not documented on the server, the only other option is you can, I don't know, reverse engineer and try to understand what the behavior is. So this is why we do testing, or you can contact them. And so where was I? Yes. If we keep retrying constantly, we're just generating more load, more traffic for the server, and probably you're making the situation worse. So what you will do is you can cap the number of retries to a somewhat small number. You can start with 3. And then you also have to pick the right timeout value. Picking the right timeout value also depends on your business logic. So if you have a user who's waiting for that data, on average, the attention span on a website is 3 seconds, and then they will just change and move somewhere else. But if you have like a service to service, you can afford a little bit longer timeouts, but you also have to be cognizant of the fact that your service might be just a node in a chain of different calls, okay? And the node before you might have other timeouts, and the node that you are calling has other timeouts, and maybe they are calling other services, and so on and so forth. So it's something that you have to take into consideration. So once we have decided how many calls we make, it's about to figure out how often we make these calls. So the first option is we just make a fixed, we pick a fixed delay, but we might end up retrying so quickly. And so we are not giving enough time to the server to just do whatever they have to do, like restart or getting rid of the excessive traffic. The other option is exponential backoff, which basically means increasing the delay between calls exponentially. You usually double it, or you use some kind of like power function. There is just a caveat here: is it can happen if multiple clients are using the same backoff strategies and they're calling at the same time, same server, they will end up making the same amount of like delay, and then they make again the call all together, and then so on and so forth. So you don't solve anything. So the strategy here is to avoid consistency, avoid determinism, and add a little bit of randomness when you're calculating the delay. It's usually called jitter, but that will probably help the server a little bit, because this is what you're doing. You're trying to help the server. This one I like it a lot. Not the slide. Well, the slide. The movie is fantastic. So suppose that, again, I like the e-commerce example because it's simple and everybody knows about that. And you click on pay because you really want whatever you're buying, but you click multiple times. And if you get charged multiple times, it's definitely not nice. So as application developers, we definitely want to avoid this type of situations. So we want to make our services to be idempotent, which means that we process the same request only once, despite how many times we receive it. So one way to achieve this is to analyze the request body that you get and generate some kind of hash out of it. The good thing is that clients don't have to do anything because it's all on the server side. But again, there's some considerations to make. First of all, your hashing has to be strong enough so that you avoid collisions. And there's also the case where multiple requests are actually legit. Suppose like a recurring payment. So that request is actually intentional because the customer is paying multiple times for, I don't know, subscription, for example.
So
yeah.
There will be not process the same request twice multiple times.
It's basically like a cache. You hash the request in some way. You might hash just part of it. You might, depends on your strategy. Mostly depends on your domain. So you have to figure it out based on your use case. You hash it based on the function that you receive, and then you have to store the hash. I'm getting there.
Okay.
Don't spoil it. I'm getting there. So the first approach is that we are trying to be polite as much as we can with the clients, so they don't have to change anything. But if, for example, we want to handle recurring payments, or we want to avoid generating the hash on our side because, I don't know, we are not confident, we have to ask the client to send us like a request ID or an idempotency. Now, it doesn't matter which approach you take, you have to store those hashes somewhere. So the first approach is you store them in memory on the node that is processing the request. It's fast, it's cheap, it works. But guess what? If another node receives the same request, process it. If the server restarts, you lose all the hashes or the IDs that you have stored. So what you do, you use a separate database, which again, more infrastructure, and there's more latency. And you also have to keep the additional cost of the data that you're storing, or maybe paying the burden of like deciding the right window for expiration. And caching is hard, like naming things. So let's get to the fourth strategy. This fourth strategy out of 100, right? So you wrote your application, it's super successful, you get a truckload of calls, and then all of a sudden, like your server begins to sit down. Some of them begin to fail. So again, first option, you just return a 500 and call it. The second is you start scaling. So upwards, outwards, depends. We talk about that. The other strategy, and we will see that in a moment more in detail, is offloading some of the work to a background worker using queues. The cheapest approach is to use rate limiting, which basically means limiting the number of calls for a specific user in a specific time frame. After the time frame, you just reset the counter and the user can start making requests. Now, if as application developers, we want to be polite to the user, we should do proper use of the HTTP statuses. I have just 10 minutes, so I've been asked to go real quick. 429, too many requests. 403, service unavailable. The first one is you screwed up. The second one is I screwed up. But the point is you can add to both of them retry after header, which is basically indicated to the user, okay, how long you gotta wait in seconds. It just has a different semantic meaning. As I said, the first one is I want to be polite to you. I'm telling you I can't process whatever you're asking right now because I'm overloaded. Just try later. And the second one is please be polite with me. Don't retry your calls until whatever it is. It can also be selective, which means that if you have a paywall, you are not rate limiting the pro user, and they get all the goods, while the people that are not paying because they're being cheap, they get rate limited. Queues, I love that. There is a lot of operations that you don't necessarily have to do. Like, for example, during user registration, you don't have to do them in your API endpoint, like sending the welcome email, generating a dashboard user recommendation, fetching additional data to enrich the user profile, and you do that from like third-party systems and so on and so on. So if you do that in your API endpoints, you might end up into failures because you have, like, I don't know, cascading failures in your upstream sources. But anyway, the gist is that you will leave your users twisting the thumb, and it's pointless. So what you can do, you can offload the work to background workers sending a message to a queue. Suppose you're working on a service that is resizing images. So you upload your images somewhere, and then you pick a list of sites for your thumbnails. The first option is you just send a message to your broker with all the resolution points, and bless you. And then you have one worker from the pool of workers pulling out the message and processing. It works, it's fantastic. We can do better. Why this is not optimal? Because if the worker fails halfway through, you just get a bunch of the images being generated, but you don't get everything. So we want the work to be atomic as possible. So the second option is we split the message and we send one message per resolution point. This works, it's atomic, but it's still not optimal because we have additional work on the client side to generate multiple messages. You have too many messages at this point generated on the broker. So there's additional work. The last option is to use something similar to PubSub. You push the single message with all the resolution points, and at this point you have a topic instead, which is a special form of queue. Topic basically is a way to distribute the same message or a slightly massaged form of the message to its subscribers. And then at this point you have a subscribers group, and each one is responsible of a specific operation, which in this case might even be like, I'm done, I'm sending an email to the original user saying, hey, we're good. And you're basically generating partitions which hold each individual subscriber groups. I know I'm probably going too quickly, but this is the last 3 slides. So there's 2 aspects that are more often than not left behind. So logging and monitoring. So knowing what happens in your system is crucial. It's not like, yeah, I wrote my code, I deployed it to my cloud, I don't know where it is, I don't care, but it's running, so I'm good. Nope. You need to know what's going on. Now, usually the cloud provider will give you infrastructure logs, which will tell you the individual network calls up to some point, but it's up to you at this point to write logs that are meaningful to you. But how do you get there? So first thing, there is nothing worse than no logs than too much, because otherwise you will be just stranded between this ocean of like too many messages and you don't know what is relevant. So what I usually do is trying to find this sweet spot, just by trial and error. And it's important at this point that you talk with your domain experts and get a sense of what is actually relevant. So for example, you had a new user registering, perfect, this is great. Let me store a log entry with, I don't know, the user ID or anything that is not breaking privacy rules. Now, an order failed, great, not so much, but still, it's something that you want to record, but you want to record not the HTTP call that actually failed, you want to record why. There was a mismatch in the warehouse, there was a shipping issue, maybe a credit card verification fail. So anyway, what I'm getting here is that logs are important, but you need to log what is under your control. So the business logic, start from there, and then you expand. And then monitoring. This is as crucial as logging. This is a non-exhaustive list of things that you should be monitoring. And it will also help you planning your scalability, because based on those metrics, you know if you can elastically or not increase or decrease the number of nodes in your cluster, which will also reduce the cost. So if you're worried about cost on your cloud provider, this is going to help you a lot. And I am done. Thank you.
Yeah,